Okay, so hi everyone. This is the first lecture on the course Analog Electronics. So mainly we'll focus on analyzing opamp based circuits, but I'd like to discuss the entire spectrum of circuits that one encounters in the entire spectrum of the analog circuits, which includes voltage regulators. And you'll see, for example, if you open up your laptop or your desktop computers, now I think desktop computers are out of fashion, or any of your cell phones and uh, iPads, you will see a board. You'll normally see a motherboard which contains all the processor chips and everything. There are different circuits that operate for different reasons on those electronic boards. Now, this course will give you a broad idea of all those functionalities that those circuits perform. Okay, so if you see, the ideas in circuits are very few, but the applications are quite large. So you'll see we'll be using very similar circuits which will look very similar, but for very different applications. So that's what this course is about. And but I'd like to introduce this course by going back 100 and almost 130 years. Okay, the course, the year we are in the year 1900s, 1902, 1901 to 5. So generally, when we talk about the 20th century, we talk about the two major inventions of 20th century. The two major scientific ideas of 20th century is the quantum mechanics or general theory of relativity. You know, both these theories, the theory of relativity was written by Einstein around the special theory was written in mid 1900s, mid 1905, around that time. And quantum mechanics, the basics of quantum mechanics, around that time, if you see in 1905, experiments were being conducted to understand the structure of an atom. Okay, so Rutherford was splitting an atom, and they were trying to arrive at a model for a structure of an atom. A third lesser known but equally important invention, which has completely revolutionized the way we live, is feedback. Okay, it's present in almost every circuit, every device that you encounter. Okay, so it's present in every device, every electronic device that you encounter. This idea, the feedback idea, is present, and most of the circuits that one encounters in practice have at least a version of feedback in them. Okay, so what is this idea of feedback? That's what I'll take you through. And if you understood this idea of feedback, the whole of the course Analog Electronics just relies on this one fundamental idea. Okay, if you understood this idea, you've understood the whole of this course. Okay, it's just we just take different circuits which use more or less different forms of feedback. So I'm just stressing the importance of feedback because I'm comparing it with, it's as big as quantum mechanics or general theory of relativity. Okay, so if you just go back 100 years, these were the big ideas. So what is this idea of feedback? So this is one of the first diagrams which was drawn by the engineer who came up with this idea called Harold. The feedback, his name is Harold Black. And this is one of the first pictures of negative feedback that he drew. Okay, and later, of course, within a few years, I think you must have heard of names like Nyquist, Bode. Those engineers, they were all mathematicians who turned into engineers. They started working on theories, how to build feedback systems. Okay, and I'll explain that idea. What was Harold S. Black working on? How did he solve it? And how is it related to our course? Okay, so that's the thing that we'll discuss in this lecture. So the problem was, so this was around 1900s, early 1900s, and most of the engineers at Bell Labs, they were working on telephone amplifiers. So if you want to make a telephone call, so you would transmit this, you will convert your speech to electrical signals. So there was a device called microphone, which would convert speech to electrical signals, and your telephones will have some internal circuitry, which will convert to a very strong electrical signal, and it will transmit it on a wire. The thing is, anytime you transmit any quantity, any electrical quantity on a wire, it experiences attenuation, loss. You know, the power slowly decreases. I mean, loss is a very normal phenomenon which even humans experience, right? If you shout, as the person moves farther away from you, your voice will be less and less audible to the person. Okay, so the attenuation is something that we also observe on our daily lives. So the farther you move away, the lesser the signal strength is, the quality of, or the strength of the signal is. The same way, the same thing applies for electrical circuits as well. If you have a long wire, you can expect the signal to be attenuated. So one quick fix for this is just amplify it. So if you have a wire between two, you come up with a distance. Okay, for this length of a wire, I'm going to put one amplifier. What does the amplifier do? It's going to boost the signal back to its levels. Because the signal level has fallen down, I'm going to boost it back, and then it's going to go back to its initial level. So these amplifiers were called repeater amplifiers. And the longer the distance you want to make your phone call, the more such amplifiers had to be placed. Okay, so there might be even hundreds of amplifiers. If you want, there were even these transatlantic cables which would run under the sea, connecting, I think, the across the Atlantic, which is United States and the British. So you would have hundreds of such amplifiers in cascade. So there was one problem with cascading these amplifiers, which is that how do you build amplifiers? So since you have done a basic course on microelectronic circuits, you know how to build an amplifier, right? So you have studied different amplifier structures. You took common source, common gate, and all that. Essentially, you will have a transistor and a resistor. The gain will be roughly, I'm just giving it a rough example. For a common source, it is minus of GM times R. Okay, I'm not considering any channeling modulation or anything. It's just some constant, which will be GM times transconductance of the MOSFET times some resistance. The thing is, these resistors and transconductors are prone to variations. So there are different variations. When you are manufacturing amplifiers, no two devices will be, there will be mismatches between two devices. On top of it, there will be variations due to temperature. Temperature can change your GM, it can change your resistor values. Then aging, as your devices age, that can also change these parameters. The transconductance again depends upon your device dimensions, mobility, and all those parameters. Okay, so those can all age, those can all change with time. So when Harold S. Black was building these amplifiers, there were no MOSFETs at that time. They were building amplifiers using vacuum tube amplifiers. Okay, vacuum tubes. If you have seen any of, since I'm assuming at least you have seen some lectures on microelectronic circuits. So they operate on this principle called thermionic emission, and it's just a three-terminal device, right? Like a switch, you can control the flow of electrons between two terminals using a voltage at a third terminal. Okay, so that's essentially a MOSFET, right? You control the flow of current between two terminals by controlling a third terminal. So when Harold S. Black was building amplifiers, at that time, the devices he was using was vacuum tube amplifiers. They were called tube amplifiers. They were pretty bulky and bigger in size, but that's not our goal now. So what was the problem he was facing? The problem was that this gain was prone to variations. Okay, this gain was prone to variations. Let's assume there is a 10% variation in gain. This is a small variation. It can be even larger than this. Assume that there is a 10% variation in gain. I'm cascading hundreds of such amplifiers. So since you're used to talking in terms of decibels, right? So whenever we mention gain, we usually express it in terms of decibels. So for example, a gain of 10 can be written as 20 log 10 is 20 decibels. So I'll express everything in terms of decibels. A 10% variation is approximately 0.8 dB. I can say approximately 1 dB variation. So which means if I'm designing an amplifier for a gain of some X decibels, you can expect some plus minus 1 dB off. Your gain will be off by 1 decibels. So just a quick question. Do you guys know why we use decibels for gains? Do you guys know why we use decibels? I can simply deal with voltage by voltage ratios, right? Why are we dealing with decibels? Any idea? So if I cascade, let's say, decibel is a relative comparison. Other advantages, let's say I take 3 amplifiers with gains A1, A2, A3. What is the overall gain? It's the product, right? A1, A2, A3 is the overall gain, the product of the 3 gains. If I express my gains in decibels, let's call it A1 dB, A2 dB, A3 dB. What is the gain of the overall amplifiers, the 3-stage amplifier? Let me express the gains as, it will be just added. That's it, right? It will be simply added. A1 dB plus A2 dB and A3 dB, so on. So that's the advantage. Decibels gives you this very simple advantage of addition of gains. Another very big reason is that generally when you're dealing with gains, the gain can vary by several orders of magnitude. Your gain can vary by, say, let's say it can be 10 power 3. Generally, when we talk about gains, they can have orders of magnitude variations. Anytime you have a quantity which is changing by orders of magnitude, we normally express them in log. Okay, express them as ratios and log. And once you express it in log, you know that log can convert exponentials to linear operations, right? So for example, if I take 10 power x, and if I take log to base 10 of 10 power x, this becomes x. So I've converted 10 power x as an exponentially increasing function, right? If I take log of that, that changes linearly. So whenever you have such huge variations, we normally express gains, huge variations, we prefer to express them in log scales. And that's where decibels come into play. Okay, decibel unit is just a logarithmic way of expressing gain in log units. Okay, it's very useful because one, you can simply add the different gains. Okay, if there is attenuation, you can subtract. So, and other advantages, you are dealing with a large scale of values. Okay, so I'll come back to this, the problem what Haroldus Black was facing. So now I said that you can expect, let's say, 1 decibel of change in gain. Your gain changes by 1 decibel per amplifier. I have cascaded hundreds of such amplifiers. So what do you think will be the overall change? Let's assume I've cascaded 100 amplifiers. 100 such amplifiers. Assume it's a transatlantic cable and it has every maybe some distance. Let's assume few meters. I'm going to place, or few tens of meters, I'm going to place amplifiers. Okay, and these amplifiers gains vary by 1 decibel. If each amplifier's gain is varying by 1 decibel, what will be the overall variation in gain at the end of 100 cascade? It will be 100 dB, plus minus 100 decibels. 100 decibels is a huge change, right? 100 decibels, if you convert it back to linear units, just think how much is 100 decibels? 20 log of, let x be the gain, equals 100 decibels. That will be 10 power 5. So your gain of these amplifiers, the cascaded amplifiers, can change by a factor of 10 power 5, right? That's a huge change. Now, what is the problem with such a huge change is that if you over-amplify it, if you over-amplify your signal, what will it do is it end up saturating. Amplifiers generally have a limit. They cannot operate on very low signal levels. Similarly, they cannot operate at very high signal levels. So usually there is something called dynamic range. Okay, so we'll not worry about that right now. For you to understand it, think that there is a minimum level for which the signal can amplify properly, and similarly there is a maximum level for which your amplifier will behave like an amplifier. It will give you perfect amplification. Okay, otherwise it's not going to give you right amplification. Okay, so there is a problem of oversaturating the amplifier. So if your gain can change by 10 power 5 times, you might end up over amplifying your signal. Okay, so when you over amplify your signal, you end up saturating the amplifiers. So when you saturate amplifiers, they become nonlinear. When your amplifiers become nonlinear, then you don't hear the speed signals accurately. Okay, so that's one problem, and this was a big issue. Okay, so what was needed when Haroldus Blank was working on this was he needed to come up with a way of designing amplifiers whose gains were relatively constant. I cannot even tolerate 1 decibel. I wanted much lower variations. I've assumed 10% variation. Can I make it 0.01% variation? Okay, so that I bring down which is a 1000x reduction, right? From 10% variation, can I bring the variations in gain to 0.01%? If I do that, then maybe yes, I can say that even if I cascade 100 amplifiers, I can still live with some margins. Okay, so this was the problem that he was dealing with. On top of it, there was also nonlinearity, two problems that he was dealing with. And it seems that he used to take a ferry, a boat, to his office. He was working for Bell Labs. I'm not sure if he was working exactly at Bell Labs, but to his office, he had to take a ferry. And on the way, he had this New York Times paper. And on the newspaper, he drew this figure, with the figure that's shown here. Okay, I won't tell you exactly what he drew, because it's been like, when he worked on it, it's been almost 100 years. So I'll tell you what the idea is, and then we'll see what he drew made sense. Okay, so what he did was, instead of feeding a signal directly at the input of the amplifier, he thought, I'll take some output, a residue of the output, a part of the output, beta, and then feed not the input, but the difference of these two. I'm going to now feed a part of the output back at the input. If I do that, what happens? So he quickly assumed, he used different notations. He called mu as the forward path gain and all that. So, and mu, b, and all beta and all that. So let's not stick with this notation. I'll just call the notations which we are used to, right? So we are used to using forward path gain as A and feedback path as beta. So I'll use this notation. So if you are given an amplifier like this, where the output is fed back, a part of it is fed back to the input, you can just write some equations to this. And because you have done control systems already, I can directly write the total gain is A by 1 plus A beta. Okay, I'm taking a part of the output and feeding it back to the input. If I do this, now what I can do is that I can express my gain in this format. A by 1 beta becomes my gain, and I'm going to call this gain as ACL, closed loop gain. Okay, since you have already done control systems, I'm just using this terminology here. So A closed loop is given by A by 1 plus A beta. And then if I take A beta common out, I can express this as 1 by beta into 1 by 1 plus 1 by A beta. Look at this term. Now, he said that his thought process was simple. He said, now let's make A as infinity. If I make A as infinity, then what happens to the gain of this amplifier? This gain, A by 1 plus A beta, becomes beta, 1 by beta. So this amplifier, feedback amplifier, gives me a gain of 1 by beta. And if I choose my beta to be, say, 0.1, then I get a gain of 10. If I choose my beta to be 0.01, then I get a gain of 100. Okay, so all I need is, if I can ensure that my beta is constant, that doesn't change, then I have in theory built an amplifier which can give me no variations at all. Now, how do I get a beta which is independent of variations? Let's take a very simple, he just took a resistive network. Let's assume R1 and R2. So then beta in this case becomes R2 by R1 plus R2. So 1 by beta then becomes 1 plus R1 by R2. Okay, 1 by beta becomes 1 by R1 plus R2. Now, if you see, this gain is dependent upon the ratio of two resistors. So if I manufacture two resistors at the same place, okay, today in integrated circuits, we manufacture them very close by to ensure that they both are matched. Now, if both the resistors age together, if the resistor ages, this resistor will also age, then the ratio will always remain constant. Let's assume this resistor changes with temperature. This resistance R1 changes with temperature. R2 will also have similar variations with them, because they both are very similar type of resistors. Therefore, the ratio will always remain constant. That was his idea. Okay, so he said, if I have to take an open loop amplifier, I have to rely on a gain which is process dependent, which is GM times R, and GM depends upon the device physics, and resistor is a different device, and your gain is now a function of two different devices. Okay, so Therefore, it's prone to process variations. Instead, he built an amplifier. He just drew this circuit and suddenly saw that I can get a gain where the gain depends upon ratio of two resistors. Okay, two very similar quantities, two very similar devices. Sorry, two very similar devices. So as they age, they both will age together. If there is any temperature variations, both the resistors will have similar variations. Okay, therefore, the variations in the gain now becomes much lower. That was his idea. Okay, so now I can use this as an amplifier and cascade it. So that's what I've written here. Here I've assumed A as infinity. When I'm deriving this result, I assumed A to be infinity. So if I substitute A as infinity in this equation, A by 1 plus A beta becomes 1 by beta. Okay, so if I substitute A as infinity, you just get 1 by beta. And in this result, the closed loop gain becomes 1 by beta into 1 by 1 plus 1 by A beta. So I'm just writing it in this format. You will see why I'm writing it in this format. You'll appreciate it better. Let's assume for the time being that A beta is much greater than 1. Okay, so remember, to get this result, your closed loop gain to be equal to 1 by beta, the most important condition that has to be met is your loop gain. I'm using the word loop gain, which is nothing but the gain of the forward path and the feedback path, product of the two, should be much greater than 1. If you don't satisfy this condition, we don't get the benefits of feedback. You have to satisfy this condition. If you do this, then your gain becomes approximately 1 by beta. So since A beta is much greater than 1, I will just express the closed loop gain in this format. So your closed loop gain can be written as 1 by beta 1 plus 1 by A beta. I've just used 1 by 1 plus x as 1 minus x. I've just used it as an approximation. This is an approximate result, which is very valid if your x is much lower than, which is close to 0 or much lower than 1. I can use this expression. Now I have gotten a gain expression, which can be expressed in terms of the loop gain. Now look at this expression and compare it with open loop gain. Your open loop gain was built, let's A1 be the open loop gain of an amplifier. You have designed it to achieve a gain of, say, 100. Okay, and this is an open loop gain. The variation in this amplifier gain will be 10%. Okay, so if you've designed it for a gain of 100, you might expect either 110 or 90. That's something you can expect. On the other hand, using negative feedback, I'm going to introduce an amplifier here in the loop such that the product A beta has to be much greater than 1. Now, how do I choose A? For example, let's say I want a gain of 100. So what should be your beta? If I want a gain of 100, what do you think should be the value of beta? A closed loop gain should be 100. What do you think should be beta? Can I say 0.01? So beta has to be 0.01. Okay, so if beta is 0.01, then you get a closed loop gain of 100. And A beta has to be much greater than 1. If A beta has to be much greater than 1, what does it mean? Your A has to be much greater than 100. So let's choose A of 10 power 5. I'm choosing 3 orders of magnitude higher than 100. Okay, if I choose 10 power 5, now let's come back to this result. I'm just trying to calculate, what am I trying to do with this analysis is that I'm trying to show you, if you took an open loop amplifier with a 10% gain variation, then the gain variation delta A by A, delta A1 by A1 is going to be 10%. Into 100 is going to be 10%. In closed loop, that variation will come down significantly. That's what I'm trying to arrive at here. Okay, so that's the point I'm trying to arrive at here. And Harold S. Black's whole idea was the same. He wanted to arrive at that result using this negative feedback amplifier. So if you see, your closed loop gain is simply given by 1 by beta into 1 minus A beta, and you can calculate delta ACL by ACL, which is nothing but the variation in closed loop gain. That is simply 1 by A beta. Okay, so this is a very interesting result. If I calculate percentage variation, It is simply 1 by this. Now, what does this result tell you is that the larger I choose A, the larger I choose my forward path gain, the lesser will be my forward path gain variation, the overall closed loop gain variation. That's a very interesting result. Now, remember, we are 100 years past when Harold S. Black first wrote this problem. Now it looks very obvious to us, but those guys were building large amplifiers. And when he when he published this idea for the first time in Bell Labs and he discussed with his engineers, they were skeptical. They said that you want to build an amplifier with a gain of 100, right? 1 by beta is 100. But to build that amplifier, you are building another amplifier with a gain of 10 power 5. How does that make sense? Because you're wasting so much gain. So they felt you're throwing away gain for what? And he said, I'm throwing away all that gain because I can achieve very good, very low sensitivity, very low variations with process. And he said, look at this expression. The larger the gain I'm going to choose in the forward path, the more will be, the less will be my variations of the gain. This was one of the cornerstones of the feedback theory at that time. So first, engineers didn't accept it because they couldn't digest the idea that to build an amplifier with a gain of 100, you have to build an amplifier with a much higher gain. Okay. So, and initially it was met with skepticism, but within a few years, as I said, within 5-6 years of Harold S. Black's publication, Harry Nyquist, I think you must have heard of this name Nyquist sampling and all that. So he wrote his famous control theory ideas on how to design stable amplifiers with feedback. And a few years later, Heinrich Bode, again, he developed plots, which now we call it famously the Bode plots, the theories for how to design such amplifiers. Okay. So in this course, we will not worry about designing those amplifiers, how to design. So here, how to design these high gain amplifiers. That is not our concern here. In this course, we will use this idea and build some very interesting circuits, okay, which can do a wide range of operations. Okay, that's what we're going to do. So we can do, I have just shown an example of feedback. What is the benefit? What was the reason? What was the motivation behind Harold S. Black's idea? But you can do crazy stuff with this very simple idea called negative feedback. Okay. The benefit it gives you is that it gives you constant gain. That's what he thought, but you could do a lot more with it. What is it that you can do? So I'll start with a simple negative feedback circuit that looks like this. As negative feedback amplifier has to have the capacity to subtract 2 signals and then amplify it by a large amount. Okay, so this operation is needed. I need an amplifier, so I cannot just rely on just an open loop. See, this is usually a single input, single output circuit, where it just amplifies a single-ended input. But I'm using the word single-ended because since you've already taken ADVD, I'm just using the word. So what here you need is you need to amplify the difference between the input signal and the feedback signal. You need a circuit which should amplify the difference between the input signal and the feedback signal with a very large gain. This hypothetical device which will have 3 terminals. And these 3 terminals are, you will amplify 2 signals, V1 and V2, the difference between the 2 signals by a huge factor. So this 3-terminal device, I'm going to call it, it's actually a high gain amplifier. We're just, in this course, it will be called as opamp. But let's call it an extremely high gain amplifier. This is a hypothetical device where A is much greater than 1. It's going to amplify the difference between the 2 signals. Okay. If you have this device, I will show now that you can build a wide array of interesting circuits. Okay, using the idea of negative feedback. So what happens? First, very simple rules. In negative feedback, any negative feedback circuit, okay, in any negatively feedback circuit, if your A is infinity, if your forward path gain is infinity, then what happens here? What happens if your forward path gain is infinity is that your feedback signal becomes exactly equal to the input signal. Now there are you can very easily show this mathematically. You can show that the error signal here, let's call E here as Vi minus Vf. And you can easily show this will simply be equal to Vi by 1 plus A beta. I'm not even going through the math. It's very easy to show that. The error signal here is simply Vi by 1 plus A beta. And if A tends to infinity, the error signal goes to 0. So the error goes to 0, which means your input signal will be forced to be equal to the feedback signal. Okay, Vi will be equal to Vf. This is one of the most, and again, and a very important result. This follows from negative feedback. This Vi equals to Vf is something that's enforced by the act of feedback. This happens only if your A is infinity. Okay, otherwise, or as long as A beta is much greater than 1. Okay, your error becomes very small. So keep this result in mind. We will be using this. This is the result based on which, see, after a point when you're learning for the first time, I know I'm repeating a lot of points here, but my intention is when you absorb this point for the first time, you have to understand all the implications of it. Then after that, we will be solving much more complex circuits, and we'll use this result. It'll become like instinct for you, right? For the first time, it's you spend time learning it. After that, it's just instinct. You just use it. You already know. You won't even think about it. What's happening there? Okay, so that's it. So Vi becomes equal to Vf. So if you take this hypothetical opamp, this high gain amplifier circuit, and if you know that this circuit is in negative feedback, you have configured it in such a way so that it's in negative feedback. And I'll tell you what negative feedback is right now. Is that since I'm repeating this point because you have already learned in microelectronic circuits, as a circuit is said to be in negative feedback if at any point you try to increase the voltage at some point, the circuit should react in such a way such that it tries to oppose that change. If I try to increase this node voltage, then if you break the loop here, if you break the point here and try to increase, if you yank this node slightly higher, you increase this, then the circuit should try to decrease that node voltage. Then you say that the circuit is in negative feedback. Okay, so you can see that if you try to increase this node by, let's say, if you increase this node, this is just a constant beta, this node will increase, but there is a minus sign here. So when it comes here, this node will decrease. So this node will also decrease. So I began by increasing this node, but the circuit responds by decreasing it. So now I know it's a negative feedback. Okay, so that's one way of testing it. So all I'm saying is, if you know that you have an opamp circuit, a circuit which consists of this hypothetical device, a high gain amplifier, or we are calling it as opamp. If you have this circuit and you know the circuit is in negative feedback, then you can easily see that you can easily use the result that V plus equals V minus. So I'm using the word V plus for this 3-terminal device. The positive input terminal, I'm calling it as the non-inverting terminal as V plus, and the negative terminal as the inverting terminal. So this is inverting terminal. This here is non-inverting terminal. So that's V plus, and this here is V minus. Okay, both the terminals will be equal. When the circuit is configured in negative feedback, this holds true only when it's in negative feedback, that V plus will be equal to V minus. And we will be using this result throughout the course to solve any opamp based circuit. Okay, so that's why I'm taking some time to stress this. So this result, the inverting and non-inverting terminals of the opamp, of this 3-terminal high gain amplifier, I'm using the word opamp from now onwards, will become equal. Okay, so that's it. So I'm here afterwards, instead of showing this summation and this gain amplifier, I'm just going to show this as a 3-terminal amplifier structure. I'm no longer going to show it as a black box. I'll show it as a 3-terminal amplifier. So that's what I've shown here. This is just your negative feedback drawn differently. So your input signal Vi is subtracted from the feedback signal Vf, which is nothing but some beta times V naught. Then you're amplifying it, which will be equal to V naught. Okay. If your A equals infinity, if your A tends to infinity, then what can you say? You can say Vi becomes equal to Vf. This plus terminal will be equal to minus terminal. and you would get beta V naught equals Vi and V naught equals Vi by beta. Okay, so that's how you achieve gain using negative feedback. So one of the simplest circuits is, how do I build beta? I just put a resistive network R1, R2, beta. Instead of beta, I put a resistive network. Then your gain for this circuit is going to be simply 1 by beta. In this 1 by beta, in this case, beta is simply R1 by R1 plus R2. And since R1 by R1 plus R, if 1 by beta is simply 1 plus R2 by R1. Okay, that's the result you get. So here I have built an amplifier with a gain of 1 plus R2 by R1. So this amplifier is called as a non-inverting amplifier. Okay, so this amplifier is called non-inverting amplifier. I'll just make one very brief point here, which is that in this course, we don't talk about how to build this device. Okay, this 3-terminal device. We don't talk how to build them. That I think you must have taught. They must have taught you in analog ADVD, or at a later stage you can find material for that. So this is a field in itself, how to build this amplifier such that it gives you very high gain over a wide range of frequencies for a wide range of input levels and all that. That's a field in itself. That's called opamp design. And again, that's a field that has matured over 100 years. Probably if I count from 1920s, then it's close to 100 years. It's little less than that. Okay, IC op-amps are little relatively new, probably 50, 60 years. But the field itself, how to build this device, that has evolved nearly close to a century, close to 100 years. Okay, so that we will not talk about that in the course. We'll assume that this device is accessible to, is available to us. And what is this device? It's a device with a very large gain, and it amplifies the difference between two signals. Okay, your output voltage is simply A times V plus minus V minus. That's the function of this 3-terminal device. Okay, 3-terminal circuit. So this amplifier is called non-inverting amplifier because it doesn't invert the input signal. Output and input signal both are in phase. So if I feed a sinusoid of some amplitude, the output signal will be exactly same in phase with this. Okay, it will be in phase. The only difference is that it will be amplified by a factor of 1 plus R2 by R1. Now, I can also do some additional operations. Okay, all I'm doing is I'm exploiting this fact that if you ensure that the negative feedback is met, then the input terminal and feedback terminals will be same. Now, let's say I want to add two signals, V1 and V2. Okay, I have two signals. I want to add the two signals. What is the simplest way to add two signals? Using two resistors. I can just take two resistors R and R. Let's assume two signals R and R. If I tap the voltage at the center of the two resistors, that will be the average of the two voltages, V1 plus V2 by 2. Again, this is very trivial to show. You can assume V2 is 0 and find this node voltage. You will get V1 by 2. Similarly, you can assume V1 is 0 and find this node voltage. You will get V2 by 2. Add the two, you get this result. V naught equals, the output here equals V1 plus V2 by 2. Now, after this, once you get a half, I can then put a amplifier to multiply it by a factor of 2, then so that I get a final output of V1 plus V2. So that's what I've shown here. I'll take two signals V1 and V2, use a simple resistive divider to add them. Okay, a resistive network to add them, and then pass it through a negative feedback amplifier with a gain of 2. And now I get a very accurate addition. V0 will be equal to V1 plus V2. So that's what I've shown here in this circuit. So if you see this part of the circuit is a non-inverting amplifier. And the non-inverting amplifier, the beta here, the feedback network here is half, right? So it's two resistors, a resistive ladder with two similar values. That will just be half. So this node voltage will be V0 by 2. So if this node voltage is V0 by 2, this node voltage is V1 plus V2 by 2, what does negative feedback do? It forces these two node voltages to be same, right? It forces these two to be same. So you get V0 by 2 equals V1 plus V2 by 2. So your V0 equals V1 plus V2. Okay. So that's the result you get, which is sum of two signals. So I've built a circuit which can add two signals. Okay. And this is a non-inverting adder. But you can also do that in a more interesting way. If you have this three-terminal device, you can also do other interesting amplifications and additions. We'll see a different form of a circuit. So I've taken this three-terminal device and connected one terminal to ground. Okay. I just forgot one point to mention one point because we are spending some time understanding op-amps, understanding feedback here. Yes. So I said this result is the cornerstone of negative feedback, which is V plus equals V minus. The positive and negative terminals, the summing point, right? The voltages at the summing point will both be identical, will be equalized. And that feedback ensures that they both are equal. You can also look at it this way. If you know that the circuit is going to have some finite output, V0 is finite, okay? Because in assuming that it's a stable system, if for a stable system, they obey this property called bounded input, bounded output. So if your input is finite, output is also finite. So if your input is finite, output should also be finite. For you to have a finite output, if your gain is infinity, if your A tends to infinity, okay? If A tends to infinity, what should be the error here? Output is finite. The gain is infinity. What do you expect the input of this amplifier to be? So you have some amplifier whose output is some finite voltage, some Vx. What if the gain here is if I say that the amplifier's gain is infinity, what should be its input? It's a linear circuit, right? I can just simply do Vx by A. Can I do that? So what will be the input? You guys are following this or?
So it be 0.
Exactly, it will be 0, right? So this will be 0. So if because this gain is infinity, because if you have any non-zero value, any finite non-zero value, multiplied times infinity will be infinity. Output will just blow up. That cannot happen. For the output to remain at a finite value, the input has to be 0, close to 0. If A is really large, it will be close to 0. That's it. That's how the error vanishes to 0. Even without the math, you can just use some intuitions to arrive at this condition, which is V plus equals to V minus or Vi equals Vf. This is the result. And you see here, that's what I did here. I mean, I just used that result here to derive this expression, right? So all I did was, I know this is V0. So this node is going to be V0 by 2. And this node here is V1 plus V2 by 2. I just equated the two because I know the circuit is a negative feedback. How do I know? It's the signal from the output is fed back to the negative terminal. Okay. So if I try to increase this node voltage, what will happen? This node voltage will increase. Since it's negative, this will decrease. So the circuit is a negative feedback. So then the moment I know the circuit is a negative feedback, I can apply this rule. What is that? That the V plus will be equal to V minus. So you can apply this only when the circuit is in negative feedback. You will encounter at a later stage in this course, you will see there are circuits which will not be in negative feedback. I mean, op-amps, there are circuits which we will be building, which will use a different kind of feedback, which won't obey this rule, but are very useful in some applications. Okay. So we'll come back to that at a later stage. So now, after having said this, I just took a small detour. I discussed two amplifiers using this hypothetical device called opamp. The first amplifier is a non-inverting amplifier, which just gives you a huge gain, okay, which is given by 1 plus R2 by R1. The second circuit I discussed is an adder. I can add two voltage signals, V1 and V2, using this. Okay, I did some cheating here. It's not really adding using opamp. I just applied an input of V1 plus V2 by 2. Okay, I already applied an average of 2 signals. So I didn't really use feedback to do any additions here. But we'll show that there is a circuit where we can do the using feedback itself, we can show this. Okay, so that's to do that circuit, to understand that circuit, you have to start with a very simple circuit like this. So what I've done here, I have not fed input at the positive terminal. I'm not doing that. Okay, the positive terminal is at ground. I'm taking my output and feeding back a part of it to the inverting terminal. And yes, because I'm feeding it to the inverting terminal, there is negative feedback in the circuit. The moment that you know that the circuit is in negative feedback, what can you tell me? What will be this node voltage? What will be V minus here? 0. Is that right? Because it's ground, right? This is ground. So this will also be ground. V plus equals V minus. So this will also be at ground. So the moment I know this is at ground, now it's a very simple circuit to solve. You can just use KCLs and KVLs and solve this circuit. So there is another property which I forgot to mention. This hypothetical 3-terminal device, which has exceedingly large gain and amplifies the difference between the two voltages, also doesn't draw any current at the input. Okay, the input terminals don't draw or supply any current. They can't do that. So the current here is 0. This is another condition. Okay, the amplifiers, which I mean, what they will teach you. And initially, amplifiers were built using BJT circuits. So those BJT circuits used to draw some input current. Okay, so generally those input currents, we call them offset currents and all that. But for the time being, I'm going to ignore that. I'll assume that right now in CMOS amplifiers, we don't worry about them. But in BJT amplifiers, initially, that used to be a concern. So that had to be taken care of. So right now, I'll assume that the input currents are 0. Okay, the amplifier is not drawing any input current. So if we use that result, all the current that flows in this resistor at this point has to flow through the resistor R2. That's it. You just equate the two currents and you have your answer. So that's like applying KCL, Kirchhoff's current law, at this node. So VI by R should be equal to 0 minus V naught by R. So R2, okay, R1. And you end up getting V naught by Vi equals minus of R2 by R1. Okay. So I did a slight modification and connected one terminal to ground. And I put a resistor like this to the non-inverting terminal, and I got a very interesting circuit. A circuit whose gain is minus of, again, the gain is ratio of two resistors, but with a negative sign. So this amplifier is called an inverting amplifier. Okay. So this amplifier is what we call an inverting amplifier. Now you can draw a mathematical model for the circuit and arrive at this result, which is what I have done here, because when I started the course, I started with a feedback model. How do I draw that? The another thing which I did not tell at the beginning is that the output terminal here, the output voltage here, V naught, is determined by A times V1 minus V2. Or I'm assuming this is V1 and V2, or V plus minus V minus. A times V1, V plus minus V minus. If I connect a resistor here and connect some other node voltage V3, this node will be not dependent on V3 at all. In other words, see, I'm just saying that if I try to perturb this node using a different source, all I'm saying is the amplifier's output will not respond to that. Electrically, I can use the word the circuit has 0 output impedance. The output impedance is 0. It means that your circuit is not going to respond if you try to perturb it from using some external voltage. Okay, so I'm using the word output impedance because I've already gone through ADVD, so I don't have to spend time. So, and that makes sense, right? So if you connect a resistor R here and the output impedance is 0, what will be the potential? The potential division ratio will also be 0, right? So let's call it R out. The voltage at the output due to the external source is going to be R out by R plus R. R out by R plus R out times say V3. Since R out is 0, this output will be 0. It simply means that if I try to perturb this or change this node voltage externally, other than these two inputs, okay, it will not change. That's what this is telling me. So that is another property to keep in mind. The output impedance of an ideal op-amp is 0. Okay, input impedance is infinity or the current is 0. So these are the properties. If you keep, again, I'll revisit these properties again in the next lecture. But once you get these properties in just 2-3 lectures, then you can just very easily analyze op-amp circuits. Just by looking at it, you'll be able to solve the circuits. You don't even have to. Right now, I'm using all KCLs and KVLs to write these equations. At some point, you won't even do all that. You'll just directly look at a circuit and guess what the output will be or understand what it's doing. Okay, and or if you're simulating a circuit, you will understand what's actually happening. So we'll come back to this. I'll show this mathematical modeling. I wanted to discuss one other point, but I think it's the time is up. I planned for 50 minutes. I didn't want to exceed the time. So let me just finish by discussing this. I'll stop it. I'll open it for 10 minutes of doubts. Okay. So if you look at this node, okay, the circuit at this node, what's happening here is you have something like this. You have I can just draw the circuit this way. So this is R1, this is R2, and this is Vi, and this is V0, and this terminal is V minus. Okay, this is V minus here. I'm connecting it to this. I need to find out what is this node voltage. So what is that node voltage? I can simply use superposition like we did before and calculate it. And that V minus is going to be Vi into R2 by R1 plus R2 plus V0 into R1 by R1 plus R2. I mean, this you can derive by applying superposition. Assume Vi is 0, find V minus. Then assume V0 is 0 and find V minus, add the two voltages. You will get this term. So now once I get this term, I have to just equate it to 0 because your non-inverting terminal is at ground, is connected to 0 volts. So if you equate this to 0 volts, you end up getting V0 equals minus of R2 by R1 Vi. I've just shown the derivation in a different way. And what is happening here, I've just drawn a block diagram representation. What you're essentially doing, V minus is actually summing two voltages. It's taking V0 and multiplying it by this factor R1 by R1 plus R2, and Vi multiplying by this factor and adding the two. That's what is V minus. And the input terminal of this differential of this op-amp is connected to ground. Non-inverting terminal is connected to ground, and I've just shown it here. So if you again use control theory, just a block diagram representation, you will get the same answer. You will get this result. Just different ways of solving this, because this is a very useful circuit, and you will see this circuit throughout the course. Okay, so analog electronics is filled with inverting amplifiers. In fact, inverting amplifier is more popular than non-inverting amplifier, and there is a reason for it, which will become very obvious to you. The reason inverting is popular, once you do ADVD, which is once you design op-amps, it will become very obvious. But right now, you can just take it from me that this is more popular than a non-inverting structures, non-inverting amplifiers. So in conclusion, what I've shown here is you can, using this 3-terminal hypothetical device and the concept of negative feedback, we can build both inverting and non-inverting amplifier. So here, non-inverting will produce the same signal amplified version of it, but they both are in phase. Inverting will produce the same signal, but one output will be 180 degrees out of phase. Okay, it will invert it by 180 degrees with an amplified version, R2 by R1. The gain is slightly higher in this case, but this has some small problems. It needs some wide input common mode range and all that. I'm using the word input common mode range because you have done ADVD. But if you don't know that, it's okay. Just think that this is more practical from an implementation point of viewpoint, or I wouldn't say practical, but I would say it's easier from a design point of view. So these are called inverting and non-inverting amplifiers. Once I have inverting, I can very easily just put another resistor. Say I've put another input. Instead of applying the single input, I can apply two inputs this way. I can connect two inputs like this, R1 and